Welcome to the deep dive. Today, we're really getting into the nuts and bolts of our computers. We're talking about how they organize and, importantly, protect all that information they store.
Exactly. Think of it like we're studying for a big test on computer internals, specifically file systems and security.
We've gathered quite a bit of material for this one. Sources covering file systems themselves, how they're actually put together, storage management.
Yeah.
The works.
Yep. And our mission, if you will, is to give you a really solid, detailed grasp of how files are organized and how those protection mechanisms actually function.
Right, because whether you're deep into tech, maybe a student, or honestly just curious about what's happening inside your phone or laptop when you save a photo, this stuff is fundamental. We'll break it down step by step.
So let's start at the very beginning, the file concept itself. What is a file?
Good question. It's basically a logical way to store stuff, isn't it? The operating system hides all the messy physical details of the disk.
Precisely. It abstracts away the hardware. So you get this idea of a named collection of related information, and it lives on secondary storage, think hard drives, SSDs.
And for us, the users, a file is really the smallest logical thing we deal with on that storage, right?
You got it. It's the basic unit. And files can be almost anything. Programs, source code, the actual runnable code.
Or just data, text files, spreadsheets, pictures, videos, all that stuff. Numeric, alphabetic, binary.
And they could be freeform, like a simple text note, or really rigidly structured, like database records.
Fundamentally, though, it's just a sequence of, bits, bytes, lines, records.
It could be any of those. The meaning comes from whoever made the file and whoever's using it. But often, the type of file dictates the structure.
Ah, right. Like a text file is lines of characters. A C++ source file has functions, declarations.
Exactly. And an executable file has specific code sections that the loader knows how to handle. The type gives it structure.
Okay, so we have these files. How does the system keep track of them all? That's where attributes come in. Like little labels?
Perfect analogy. File attributes are the data about the file. Super important for the OS and for us.
So obviously there's the name, the thing we actually call the file.
Yep, the human readable name. Then there's the identifier, usually a number, not really for us, but a unique tag for the system, the file's internal ID.
And type, which we just talked about, tells the system what kind of file it is. Crucial.
Then location, basically a pointer, tells the OS where on the physical device the file lives.
Size is pretty straightforward, how big it is now, maybe a maximum allowed size.
Right. And protection, super important. Access control. Who can read it, who can write to it, who can run it if it's a program.
And finally, the timestamps and user ID. When was it made? Last changed? Last used? Who owns it?
Exactly. All that info is vital for tracking, for security, for system management, even billing sometimes.
Okay, attributes tell us about the file. But how do we do things with files? We need operations.
Right. The OS gives us a set of basic commands, system calls usually. First, you need to create a file. Makes an empty one.
Then you write to it. You tell the system the file name and the data. And there's usually a write pointer keeping track of where you are.
Yep, the write pointer gets updated as you add data. Similarly, you read a file, you give the name, say where in memory to put the data, and a read pointer tracks your position.
And you can move that pointer around, right? Repositioning or seeking.
Exactly, seeking. That lets you jump anywhere in the file. Essential for random access, not just reading start to finish, like skipping chapters in a digital book.
Makes sense. Then there's deleting a file, gets rid of the directory entry and frees up the disk space.
Right, and one more interesting one, truncating. That wipes the file's contents, makes it zero length, but keeps all the other attributes.
Huh. Okay, so why keep the attributes?
Maybe you want to reuse the file structure or permissions, but start fresh with the data. These basic operations are the building blocks for everything else we do with files.
Now often, before we read or write, we have to explicitly open the file first. Why that extra step?
The open call. It's really important. It tells the OS, hey, this process is going to be working with this file. The OS then sets things up internally.
How does it set things up?
It uses something called the open file table. It's a system-wide list of all currently open files, but it usually has two parts, two levels.
Okay, what are the two levels?
First, there's a per process table. Each running program gets its own little table listing the files it has open.
And what's in that per process table?
Things specific to that process's interaction with the file, like its own current file pointer, where is this process reading or writing? Also the access rights this process requested, read-only.write. Maybe some accounting info.
Okay, so each process has its view, What's the second level?
That's a system-wide table. This holds info about the open file that's independent of any single process. Stuff like the actual disk location of the file, access dates, the file's current size.
And this table is shared.
Yes, and crucially, it contains an open count for each file.
An open count? What's that for?
It tracks how many different processes currently have that same file open. It's vital. The system only truly closes the file resources when this count drops back to 0.
Ah, I see. So multiple programs can use a file, and the system knows not to pull the rug out until everyone's done.
Exactly. Prevents chaos.
So recapping the info associated with an open file, we have the file pointer.
Per process file pointer, yeah. Tracks the next read-write spot for that specific process.
The file open count.
System-wide. Tracks how many processes have it open.
The disk location.
Usually cached in memory when opened. Faster access than going to disk every single time.
Smart. And the access rights.
Also per process, based on how that process opened the file. Did it ask a read-only? Read-write? The OS enforces those rights on subsequent operations.
Okay, that covers opening files. Now, how do we actually get the data out? The access methods.
Right, different ways to get at the information inside. The most basic is sequential access.
Like reading a tape. Start at the beginning, read block by block.
Pretty much. You process the info in order. Read next, write next. Simple editors, compilers often work this way. They just process the file from start to finish.
Makes sense. But what if I need, say, record number 500 in a huge database file? Reading everything before it would be slow.
Terribly slow. That's where direct access, or random access, comes in. The file is seen as a numbered collection of fixed-size blocks or records.
So I can just say, give me block 73.
Exactly. Read 73 or write 25. You can jump anywhere directly. Databases rely heavily on this. You need to fetch specific records quickly based on some key.
Okay, sequential and direct. What about other access methods?
Well, those usually build on top of direct access. Often, they involve using an index.
An index, like in the back of a book?
Kind of. It's a separate structure that maps keys, maybe an employee ID or product code, to the actual block number on disk where that record lives.
So you search the index first, which is hopefully faster or smaller, find the key, get the block number,
and then use direct access to jump straight to that block. Much faster for finding specific things in large files than scanning sequentially.
And you can have indexes on indexes, like multi-level.
Yep, for really huge files, you might have a primary index pointing to secondary index blocks, which then point to the data. It helps manage the complexity.
Got it. Okay, so we know how files look logically and how we access them. Let's get into the implementation details. How does the OS actually put the file's data onto the disk? Allocation methods.
Right. This is about how disk blocks get assigned to files. 3 main ways: contiguous, linked, and indexed.
Let's start with contiguous allocation. Sounds like what it means, all the blocks together.
Exactly. All the blocks for a file occupy a single continuous chunk on the disk, like reserving a whole row of seats together.
So the directory just needs to know where the file starts and how many blocks long it is.
Precisely. The starting block address and the length. That's it.
What's good about that?
Performance. Sequential access is super fast. Just read one block after the next physically. And direct access is also easy. Want block in. Just add n to the starting address. Simple calculation.
Okay, sounds efficient. What's the catch?
Fragmentation. Specifically external fragmentation. As you create and delete files, you end up with lots of small, unusable gaps scattered across the disk.
Ah, so you might have enough total free space for a big file, but no single contiguous chunk big enough.
That's the classic problem. You can try to fix it by compacting the disk, shuffling everything around to consolidate the free space, but that's a huge, slow operation.
And how do you even know how much space a file will need when you first create it? Files grow.
Another excellent point. If you guess wrong, you're stuck. One workaround is using extents. You allocate an initial chunk, and if the file grows, you try to find another contiguous chunk and link it somehow. But that adds complexity.
Okay, contiguous is simple but problematic. What about linked allocation?
Linked allocation throws contiguity out the window. File blocks can be scattered anywhere on the disk.
Anywhere? How do you find them all?
Each block contains a pointer to the next block in the file. It forms a linked list. The directory entry just stores the address of the very first block and maybe the last.
So to read the file, you start at the first block, read it, find the pointer inside it, jump to the next block, read it, find the pointer, like a chain.
Exactly like following a chain. When you write and need a new block, the system grabs any free block, adds it to the end of the chain, and updates the pointer in the previous last block.
The big advantage must be no external fragmentation, right? Any free block will do.
Spot on. And files can grow easily as long as there's any free space. You don't need to pre-allocate.
But direct access must be a nightmare. To get to block 50, you have to read blocks 1 through 49 first, just to follow the pointers?
You hit the nail on the head. Direct access is very inefficient. It's really only good for sequential reads.
What else? Any other downsides?
Yeah, the space used by the pointers themselves, it's not data space. And reliability, if one pointer gets corrupted, you could lose the rest of the file.
Ouch. Are there ways around that?
People have tried things. Doubly linked lists help with recovery. Storing the file name or block number in the block can help too. But a major variation is the file allocation table, or FAT.
Ah, FAT, like FAT32 from older Windows versions and USB drives?
That's the one. Instead of putting pointers in the data blocks, FAT puts all the pointers together in one big table at the start of the disk volume.
How does that work?
The FA table has an entry for every block on the disk. The directory points to the first block of the file. You look up that block's entry in the FAT, and it tells you the number of the next block. You follow the chain within the FAT table itself until you hit an end-of-file marker.
So the pointers are centralized. Does that help with direct access?
It helps a little with management. Maybe caching the FAT is easier, but fundamentally you still have to traverse the chain in the table for direct access. It doesn't solve that core inefficiency.
Okay, so FAT is a variation of linked. What's the third method? Indexed allocation.
Indexed allocation tries to get the best of both worlds. Each file gets its own special block called an index block.
An index block, what's in it?
It's just an array of pointers. The first pointer points to the first data block of the file, the second pointer points to the second data block, and so on. The directory entry points to this index block.
I see. So if I want the 10th block of the file, I'd go to the index block, look at the 10th pointer, and that tells me exactly where the 10th data block is on disk.
Precisely. Direct access becomes very efficient. Just one lookup in the index block gets you the address. And there's no external fragmentation because the data blocks themselves can still be scattered anywhere.
That sounds pretty good. What's the downside?
Overhead. You need that extra index block for every single file, even tiny ones. And a single index block has a limited size, right? So it can only hold so many pointers.
Right. What happens if a file is huge and needs more pointers than fit in one index block?
Good question. Couple of strategies. You could link index blocks together. The first index block points to data, and maybe its last entry points to a second index block.
A linked list of index blocks.
Yeah, or you can do multi-level indexing. The main index block doesn't point to data blocks, it points to other index blocks, and those point to the data blocks, like a tree.
So like a first level index points to second level index blocks.
Or which point to data. Or even third level for massive files.
Is this related to how things like inodes work in Linux or Unix?
Very much so. Inodes use a combined scheme that's really clever. The inode itself, which is like the index structure, holds the first few, maybe 12 direct pointers to data blocks.
So small files are super efficient. Pointers are right there in the inode.
Exactly. Then, if the file gets bigger, the inode has pointers to single indirect blocks, which point to data. Then maybe a pointer to a double indirect block, points to single indirect blocks, and even a triple indirect block.
Wow, okay. That scales really well from tiny files to enormous ones while keeping direct access reasonably fast.
It's a very effective compromise. Handles most cases efficiently.
Okay, allocation methods covered. Now, how are the files themselves organized so we can find them? Directories.
Right. A directory is basically just a special file that contains information about other files and maybe other directories, subdirectories. They live on disk too.
And we do things like search them, create files in them, delete from them, list what's inside.
Rename things, move between them.
Yeah.
Yeah. The main goals are efficiency, finding files fast, convenient naming, letting users use the same name in different places, maybe linking, and logical grouping.
Grouping is key for humans, right?
Yeah.
Keeping related stuff together.
Definitely. So you have different structures. The absolute simplest is a single level directory. One big directory for everyone.
Sounds chaotic. Everyone's files mixed together. Naming conflicts must be constant.
Totally impractical for multi-user systems. So you get two-level directories. Each user gets their own directory.
Better. Solves naming conflicts between users. You use a path like user file name. Search is faster within your own directory.
True, but users still can create subdirectories within their own space to organize projects or types of files.
Which leads us to what we mostly use today, tree-structured directories.
Exactly, the hierarchical structure. Directories can hold files and other directories.
Yeah.
You get that familiar nested folder structure. Super flexible, lets users organize things however they want.
Okay, great. Now, briefly, let's touch on storage management. Our sources mention the physical media magnetic disks and solid-state disks, SSDs.
Yep, the workhorses.
Yeah.
HDDs with spinning platters, SSDs with flash memory, different speeds, costs, durability trade-offs.
Yeah.
The sources also mention disk structure platters, tracks, sectors, the physical layout.
And then things like disk scheduling and formatting.
Right. Scheduling is about the OS deciding the best order to handle disk read-write requests to be efficient, especially with moving parts on HDDs. Formatting is preparing the disk partitioning, creating the basic file system structures.
Crucial stuff, but maybe a bit too deep for today's dive.
Yeah, we could spend a whole session just on scheduling algorithms.
Yeah.
For now, just know they're part of managing the underlying storage effectively.
Agreed. Let's shift gears to the final critical topic, protection mechanisms, keeping our data safe.
Absolutely vital. The main goal here is preventing anyone or anything from accessing or modifying resources they shouldn't, whether it's intentional malice or just a bug.
So it's about enforcing rules, making sure programs and users only use resources according to the defined policies.
Precisely. Protection mechanisms enforce policies. Policies might be fixed by the OS, set by admins, or even controlled by individual users for their own files.
And the system needs to be flexible because policies can change, right?
Exactly. It's important to separate the mechanism, the how, from the policy, the what. Mechanisms should be robust enough to support different policies.
Are there guiding principles for designing these protection systems?
A huge one is the principle of least privilege.
Least privilege. Give things only the permissions they absolutely need and nothing more.
You got it. Every program, every user, every system component should operate with the minimum set of privileges required to do its specific job.
Why is that so important?
It minimizes the potential damage if something goes wrong. If a program with limited privileges gets compromised, the attacker can only do limited harm. If it had full admin rights, well, that's much worse.
Makes sense. So OS features, system calls, even data structures should be designed with this in mind, granting and revoking privileges as needed.
Ideally, yes. And it applies to user management too. Don't run as admin all the time. Use standard user accounts. Restrict services. Limit remote access. It's about containing risk.
Okay, so we control access. This brings up the idea of a domain of protection. What's a domain?
Think of a system as processes doing things and objects, files, devices, memory, the things being acted upon. A domain is basically a context, an environment that defines what a process running within it is allowed to access.
So a domain is like a set of permissions.
Essentially, yes, it's a collection of access rights. Each right is a pair, an object name, and the set of operations allowed on that object, like file, read, write.
So a process in that domain can read and write file, but maybe not delete it unless it also has the delete right in its domain.
Exactly. The domain defines the boundaries of what a process can do at any given moment.
How are these domains actually set up? Is it per user? Per program?
It can be realized in different ways. It could be per user, you switch domains when you log in or out. It could be per process, each program runs in its own domain, maybe switching temporarily when communicating. Or even per procedure, really fine-grained switching domains on function calls.
Wow, lots of possibilities. Now, the sources introduce the access matrix as a way to model all this. What is that?
The access matrix is a really useful abstract model. Imagine a big grid. Rows are the domains, D1, D2, etc. Columns are the objects. File F1, printer, maybe even other domains.
And the cells in the grid.
Each cell, say accessee J, the intersection of domain die and object OJ, contains the set of rights that processes in die have on OJ.
So access 1, one might say read, meaning domain 1 can read object 1, maybe file F1.
Precisely. Access 2, printer column might say print. If a cell is empty, no access is allowed. It maps out all permissions in the system.
Can domains themselves be objects in the matrix? You mentioned switching domains.
Yes. If domains can switch, you might have a switch right. If access domain O, domain B contains switch, a process in domain A can switch to operate within domain B's set of rights.
Okay. And what about copy and owner rights?
Copy, often shown with an asterisk like read, lets a domain grant that specific right without the star to another domain for the same object within the same column. It allows limited delegation.
And owner sounds powerful.
It is. If domain D1 has owner right for object F1, then D1 can change any entry in the F1 column. It can grant or revoke, read, write, etc. for F1 to any other domain. Full control over that object's permissions.
Then control, that applies to domains.
Right. If domain A has control right over domain B, then domain A can remove any right from domain B's entire row in the matrix. It's a way for one domain to restrict another's overall capabilities.
So the access matrix is like the master blueprint of system protection, even if it's not implemented exactly like that grid in practice.
Exactly. It's the conceptual foundation. Real systems use things like access control lists. ACLs per object list who can access it and how, or capability lists per domain list what objects it can access, which are basically just different ways to store and manage the information represented in that abstract matrix.
Wow. Okay, we have covered a ton of ground today, from the basic file concept, attributes, operations, access methods,
to the nitty-gritty of allocation methods, contiguous, linked, indexed, and their trade-offs.
directory structures, a quick look at storage management, and then deep into protection, goals, principles like least privilege, domains.
And finally, that access matrix model tying it all together. Hopefully some aha moments in there, understanding why things are designed the way they are.
Definitely, like seeing the trade-offs between, say, linked and indexed allocation or how protection is layered.
So for you listening, maybe think about how these different access methods might affect the speed of apps you use, or how the permissions on your operating system relate back to that access matrix idea.
Right. And what about the future? With SSEs getting faster, data volumes exploding, what's next for file systems and security?
That's the big question, isn't it? As we generate just unbelievable amounts of data, how do we keep organizing it efficiently, finding it quickly, and most importantly, keeping it secure in this incredibly connected world?
A constant challenge, for sure. Something to keep thinking about.